Okay, let's talk about when zeros are significant in a measurement. Here we have four examples, 1.0, 1.00, and so on. The zeros here do count, and let me emphasize the decimal places here. When zeros follow a decimal, when they're trailing a decimal point and a non-zero, they have to be trailing both the decimal point and the non-zero, then they count in a measurement. Basically what these zeros are doing are telling us how precise the measuring instrument we used was. So for instance, if these numbers represented masses that we could read on a balance, this balance here would be much more precise than this one up here because it could read out to the tens, hundreds, thousands, out to the 10,000ths of a gram, whereas this balance up here could only read up to a tenth of a gram. So when we count the significant figures, we're counting all the digits now. So we have two significant digits here, three significant figures here, four here, and five here. So just applying this to measurements, let's suppose that we measure a mass that is exactly 1.05 grams. And we measure it on each of these balances. What is the display on the balance actually going to read for that mass? Well, the interesting thing is that if we put this mass on this balance that only can measure out to the tenth of a gram on the display, okay, this guy is going to read not as 1.05, but it's going to read as 1.1 grams. So this is going to round up to the two significant figures that the balance can display. Only when we put this mass on this balance will it read out the full 1.05 grams because it can read the full three significant figures. Okay, and this mass would on this balance would read 1.050 grams, and down here it would read 1.0500 grams. So this is where we see significant figures are very important. They're telling us about how many digits each instrument can read, which is the precision of the measuring instrument. So we're saying in here that a measurement that here can only be taken out to the tenths place. A measurement here could be taken out to the thousandths. A measurement here could be taken out to the 10,000ths. So those zeros count. They're very important. Likewise, zeros are important when they're sandwiched in between other non-zeros. We call this the sandwich rule. And this one is pretty easy to remember. So when we have zeros, for instance, 2005, this is four significant figures. There's no other way that we can rewrite this number, getting rid of the zeros and maintaining the entire value of that number. Likewise, 10,003 has five significant figures. If we take a look at some other decimal numbers, let me go back to black here. 0.00700. How many significant figures does this have? In this case, the zeros that are trailing the decimal and the non-zero, as I said before, are only the significant ones. So this example has three significant figures, okay, or 0.00001. This example only has one significant figure, okay. These zeros are trailing the decimal, but they're not trailing a non-zero. They have to also be trailing a non-zero. So 0.05600. In this case, there's four significant figures. Okay, these zeros are trailing the non-zeros as well as the decimal point. This guy is trailing the decimal point, but not the non-zeros, so they're not significant. Again, in these examples, these zeros, all of these guys, I'll circle them like that. What do we call them? We call them placeholders. Okay, they're telling us this time how small the number is. We can get rid of the placeholders by rewriting all of those guys in scientific notation. So the top example can be written as 7.00 times 10 to the minus third power. Okay, the next example can be rewritten as 1 times 10 to the minus 1, 2, 3, 4, 5 power. And the third example can be written as 5.600 times 10 to the minus 2 power. So remember, we got to keep the zeros that were significant in the original number, but we just get rid of the placeholders.